Alright, this is the unit review for Chapter 1 for Precalculus. Looking at number 1, we have a piecewise function. We need to find the values of f of 2, f of negative 2, and f of negative 4. So for f of positive 2, we have to decide which of these three domains the positive 2 fits in. So if I look at the top one, 2 is not less than negative 2, so it's not going to go in the top function. If I look in the middle function, negative 2 is less than 2 is true, but 2 is not less than 1, so it can't go in the middle function. So that means it's got to be the bottom function. 2 is greater than 1, greater than or equal to 1. So I'm going to plug 2 in to the bottom function, but there's no place to plug it in. So that means that f of 2 is just the value that I was given initially, which is 2. I'm going to do the same thing for f of negative 2. So for negative 2, I'm going to look. The top function only works when x is less than negative 2. So we're going to plug it into the middle function because it says less than or equal to negative 2. So I'm going to have negative 2 squared minus 2. And that's going to be positive 4 minus 2, which is 2 again. And finally, we have f of negative 4. Negative 4 works for the top function because negative 4 is less than negative 2. So I'm going to plug in negative 2 times negative 4 minus 4. And that's going to give me 8 minus 4, which leaves me with 4. So I've evaluated all three functions. Number 2, again, very similar. We have a piecewise function defined for three different intervals. Find the value of f of 1. So when is this function true? When do we use 1? Top one says x has to be less than 0, so that's not it. The middle one, x has to be between 0 and 1, including 0 and 1, so that's the one we're going to use. Again, that's just a constant, so there's no place to plug in the 1, so we just have a 5. F of negative 2, that's going to be true for the top function because x is less than 0. So that's a 5 minus 2 times negative 2. That's going to be 5 plus 4, which is 9. And finally, f of 1/2. 1/2, again, falls in between 0 and 1. So I'm going to get 5 again. Number 3, find the domain of the function. Remember, when we're finding the domain, we have to find the domain of the top and the bottom separately if it's a fraction, and then decide from there what the most restrictive domain is. So if we look at the top, it's a radical. We know that radicals cannot be negative, so we have to decide what values of x make that function positive. And just by looking at it, we can tell that x must be greater than or equal to positive 2, because anything less than 2 I'm going to get a negative. So we can state the domain of the top as 2 with a bracket to infinity. Do the same thing for the bottom. For the bottom, we know that we just can't simply divide by 0. So what's going to make the bottom equal to 0? Well, that's just going to be the number 5. So that says x just cannot be positive 5. So that bottom one would actually be negative infinity to 5 with the union of 5 to infinity. So when we look at these two domains separately, we just have to decide which one is the most restrictive. Well, obviously the top one starts at 2 and goes to infinity. So that means that this negative infinity part is out. But everything else seems to be okay except for the number 5 in here. So we have to combine the two domains together and say that, well, we can pick any number starting at 2 and going to infinity, but we have to exclude the number 5. So my final domain is going to be 2 with a bracket, because I can use the number 2, all the way up until 5, but not including 5, so that's a parentheses, and the union from 5 all the way until infinity. And then we look at part B, same thing. The top, There's no restrictions on the top for either parts of this function, so we're good there. So those are just all real numbers. At the bottom, again, we just care about where it's equal to 0. Well, the bottom here, x plus 2 is equal to 0 when x is equal to -2, so we know our domain cannot be -2. And for the right-hand side, x cannot be 0. Any other number works though, so my domain is going to be -infinity all the way up until -2, the union with -2 until 0, and then the union of that with 0 to infinity. So there's three areas that I have. I have -infinity up until -2, then -2 until 0, and then 0 to infinity. Number 4, simplify f of 5 plus h minus f of 5 over h. Remember what this notation means. 5 plus h just means we change our input from x to 5 plus h, and we're going to subtract what we get when we plug in f of 5, and then we divide it all by h. So I'm going to do this in steps. I'm going to first find f of 5 plus h. So I'm going to plug 5 plus h in for x, so I'm going to get 5 plus h squared plus 2 times 5 plus h. That's going to give me 25 plus 10h plus h squared plus 10 plus 2h, and it looks like I can combine that a little bit to get h squared plus 12h plus 35. Okay, so that's the first part. Then I'm going to find f of 5, which is just going to be 5 squared plus 2 times 5, which is going to be 25 plus 10, which is 35. Now I can plug it into my formula. So f of 5 plus h is h squared plus 12h plus 35 minus f of 5, which was another 35, all divided by h. Well, these 35's cancel out. I'm left with h squared plus 12h all over h. And everything has an h, which means I can cancel one h off of everything, and I'm left with h plus 12. And that's my final solution for that one. Part B, same thing. Remember, again, we're plugging in, so we need to find f of 5 plus h, and we also need to find f of 5, then we need to combine them. So 5 plus h is going to be -6 times 5 plus h squared plus 7 times 5 plus h. Give myself a little bit of room. So I'm going to get -6 times 25 plus 10h plus h squared plus 35 plus 7h. Multiply that through. I get -150 minus 60h minus 6h squared plus 35 plus 7h. Combine like terms. -6h squared minus 53h. That's going to be minus 115. Then I have f of 5, which will be -6 times 5 squared plus 7 times 5, and that's going to give me -115. So when I subtract them, so it's f of 5 plus h minus f of 5 all over h. So it's -6h squared minus 53h minus 115 minus -115 all over h. these cancel out, and because I'm kind of running out of room here, I'm going to go ahead and do the h's at the same time. Once the 1/15ths cancel out, I'm left with 3 terms that'll have an h, so I can cross those out, and I get negative 6h minus 53. Alright, looking at 5 and 6, a little reminder that when we're talking about intervals of increasing and decreasing, we're specifically talking about x values only. Okay, so domain, we know domain are the x values, so we're just looking at side to side on the graph. My graph moves left as far as I possibly want to, so that's negative infinity. There's no places in the middle where it doesn't exist. Even though we have a hole up here at positive 1 for y, it's solid down here, so it exists everything in between. And then we know that the arrow tells me that it moves right as far as we want. So our domain is negative infinity to infinity. The range are the y values. So my graph, the lowest value of my graph is right here, which is at negative 3. That's going to be a bracket because the function exists at negative 3. And it goes up forever. So that's going to be infinity. Increasing intervals, that's where the graph appears to be going up as I move from left to right. The only place where the graph is moving up is from 0 until forever. So that's going to be 0 to infinity are my increasing interval. Decreasing intervals, well, it's decreasing from negative 1 until 0. So at negative 1 until 0. And constant, it's constant from negative infinity until negative 1. Number 6, we're going to use this graph, same thing. Oop, I need to scroll down a little bit. F of 0, if we're back to 5, we have to find f of 0, f of 2, and f of negative 1. So f of 0, we look at the graph, so we know that's where, when we plug in x, what do we get? So if I have an x at 0, I follow my graph, and I'm down here at negative 3. So f of 0 is negative 3. F of 2, so I find positive 2 on my graph, go up until I touch my graph, and I'm at positive 1. And f of negative 1, at negative 1, well, I've got part of a graph up top and part of a graph below. We only care about the part that's shaded or colored in, which is going to be down here, which is at negative 2. Alright, so now on to number 6. The domain of the graph, again, if we look at it, everything exists all the way across the graph from left to right. There are no holes that aren't filled. So we have negative infinity to positive infinity for my domain. My range now has a highest point. The graph never goes above that value, but it goes low forever. So that's negative infinity until positive 5, and that has a bracket. Increasing intervals. So the graph is increasing from negative infinity up until negative 2. Union. It's also increasing from 0 until positive 2, and that's it. Decreasing intervals, so the graph is going down from negative 2 until 0, and that's the union with the other part where it's going down, which is from positive 2 till infinity. Again, looking at the graph, constant intervals, there are none. Make sure you write none. Don't leave it blank. Don't write 0. We evaluate f of 0. F of 0 is when x is 0, which my graph is at the origin, so f of 0 is 0. F of 2, so I find 2. Again, there's 2 possible values. I only care about the one that's solid or shaded in, which is at positive 5. And f of negative 2, is also at positive 5. Moving on to the piecewise functions. What I would actually suggest you do for these, you can sketch them by hand, or you can use the graphing calculator and use the graphing calculator and then use the table on the graphing calculator to make the sketch. What we're going to do real quick is, we know that we have this line 5 minus 2x when x is less than 1. That is going to be a line that crosses the y-axis at 5, has a slope of negative 2. It does not exist at positive 1, but it exists everywhere before positive 1. So we're going to have a line that looks like that, and of course it drew backwards. We have that for our first part. And then for the quadratic, we have a quadratic that is shifted up 4 units. So it crosses the x-axis at positive 1. I'm sorry, at positive 4. It crosses the y-axis at positive 4. But the function doesn't exist there. It doesn't start existing until x is 1. So we're going to have a solid dot at 1, 5. Think about plugging it in. Plug in a 1. 1 squared is 1 plus 4 is 5. The next point that will exist is at 2, 8, which is right at the tip of my graph. And it's a quadratic, so it's going to look like that. Alright, number 8, sketch this graph. Again, we have a quadratic. This is a standard quadratic, standard width, no shifts, and it exists from positive 2 backwards. So we have a point at 0, 0, 1, 1, 2, 4, and all of their reflections. So we have this, and then the bottom one is a parabola that's upside down. It's reflected and it's shifted up 3 units. But that doesn't start until values greater than 2. So if we start plugging in values, I'm going to plug in positive 2. So that gives me, when I plug in a positive 2 to this function, I get negative 1. So we should have an open circle at negative 1. Then at 3, we have negative 6. So I need to go down 1, 2, 3, 4, 5, 6. And I have a parabola here. And there's my piecewise function. Alright, number 9, we have a stepwise function. Read this just like a piecewise function. You're just interpreting the graph. It's telling you that these are speed limits based on distances in miles. Part A, what is the speed limit at the 6 mile mark? So obviously we have 4 miles here, 8 miles here, 6 miles should be right in between them, which appears to be that right there. So again, we only read the solid ones, so I'm going to go across to my y-axis, and that looks like it's about 25 miles per hour. Part B, estimate the miles of highway with a speed of 25 miles per hour. So I've got these two groups of sections here and here. So I have from 6 to 8, which is 2 miles, and then 12 to 6, which is another 4. So 2 plus 4, that leaves me with 6 total miles. That the speed limit is 25 miles per hour. Part C wants me to evaluate f of 5, f of 9, and f of 15. So we're just going to look at the graph. F of 5, so I find speed limit, or the distance of 5, we go up to our graph, and it takes me to 30. F of 9, that's going to be about right here. I'm going to go all the way up to 65. And f of 30, I don't know why I said 30. Should be f of 15. And 15 is about right here, and that's going to be back to 25. Part D, at what values is the graph discontinuous? So we didn't talk about this in class, but you can hopefully you can guess. Discontinuous means not continuous, which means we don't have a solid line. Well, it's discontinuous wherever there's a break. So there's a break where it jumps at 4. There's another one at 6, another one at 8, another one at 12, and another one at 16, another one at 20. So it's discontinuous at 4, 6, 8, 12, 16, and 20, and interpret each discontinuity. Speed change is the interpretation of that. Number 10, we have an oil well. It's leaking oil. And we have two functions. We have the radius of the oil leak is represented by the amount of time that the oil spill has been going on, which is 2t. And then we have the area of the leak, which is represented by pi r squared. This says find a of r of t. So that means we're going to plug the r function into the a function. So we got a times 2t squared. So that's going to give me 4 pi t squared. That's my composition. It says interpret. So again, like we did in class, the two things that we have now are t, which is time, and a, because we no longer have an r. So we have t, which is time, and a, which is area. So this is the area of the spill after t minutes. And see, what is the area of the oil slick after 6 minutes? So after 6 minutes, we're going to plug in 6 to t. That's 4 pi times 6 squared. Plug that into the calculator, and you're going to get 452.6 square feet. Alright, find the inverse of the function. And remember, whenever we're manipulating functions, we have to worry about the domain. So if we look at a, remember the rules for finding the inverse. We're going to replace the f of x with a y. Then we're going to switch x and y. So I'm going to have x equals y plus 2 cubed minus 4. And I'm going to continue to solve this out. So I'm going to add the 4. So x plus 4 is equal to y plus 2 cubed. I'm going to take the cube root of both sides. So the cube root of x plus 4 is equal to y plus 2. And then my last step, to get my inverse of f, is going to be the cube root of x plus 4 minus 2. And looking at the two functions, the original function is a cubic function, so it has no domain restriction, and my new function is a cube root function, has no domain restriction, so that means my domain is all real numbers. Part B. Before we even start this, I know that it's a fourth root function, so that's going to be restricted just like a square root. So we need to decide what's going to make the inside not doable. And when I look at that, x must be greater than or equal to -2 to keep me from having negative values underneath there. And my range, if we remember from translating, this is shifted up 5 units. So y has to be greater than or equal to 5. This could be helpful when we find the inverse. So again, I'm going to replace f of x with y, switch them around, so x is equal to the fourth root of y plus 2 plus 5. So you get x minus 5 is equal to the fourth root of y plus 2. raise both sides to the fourth power, so I have x minus 5 to the fourth equals y plus 2, and then the inverse of x is equal to x minus 5 to the fourth minus 2. Now the domain is going to be restricted, and it was important to say both the domain and the range of the original function, because we remember, hopefully, that when we're talking about inverses, the domains and ranges flip-flop. So the domain of my original function is now the range of my new function. If we look at this, this new function is shifted down 2 units, which means that my range would be from -2 to infinity, which makes sense because that was my old domain, and my range of my original function is now my domain, so I can say my domain is 5 to infinity. Number 12, we're looking at transformations of functions. 3 big things that happen. We have the a value out front, something inside the radical, and something outside. The negative reflects. So this graph is reflected over the x-axis. It is shifted down 2 units, and it's shifted left 7 units. Remember, the value inside is opposite. Same thing with the absolute value function. This is compressed. Remember, when a is less than 1 or between 0 and 1, it's compressed, so it means it gets wider. It's shifted right 2 units, it's the opposite direction, and it's shifted up 5. 13 says find g of x when you're shifted 1 unit to the right and reflected. Well, we know that reflecting means that it's going to be negative a, so we take x cubed, we make it negative, and then it's shifted left 1 unit, so I need to make it x plus 1 cubed inside the parentheses. And part B, g of x is equal to, let's see, it's shifted 2 units down and has a vertical stretch of 3. So stretch and compress, that's changing the a value. If it's stretched by 3, that means it can turn into 3x cubed. There's no horizontal shift, so I don't need a parentheses. It's shifted down 2 units, so that's just going to be minus 2. Alright, last page. We have, looks like a cubic graph right here, local minimum. It's going to be right there at that guy, which is at the point 0, -1. Local maximum is at the point -2 and it looks like 3. Increasing intervals, so again we're increasing and increasing. That's going to be -infinity to -2, union 0 to infinity. Remember, when we're talking about increasing, decreasing intervals, we're only talking about the x values, and we are decreasing from -2 until 0. And if we scroll down, is this function even, odd, or neither? Remember, even has to be reflected across the y-axis. Well, here's my y-axis. I'm definitely not reflected across that, so it's not even. Odd has to be reflected across the origin, which means that a point here has to exist over here. That doesn't happen either. So this function is neither. Same thing for number 15. This one I have to actually graph. So if we make it, go to the graphing calculator, plug in the value or plug in the function, and then it's actually easiest to start by finding your maxes and mins and just kind of sketch it from there. So the minimum is at -1.24, -1.63, and there's another minimum at positive 1.24 and -1.63, and there's a maximum at 0, 1. So if I'm going to change my scale to 1, 2, 3, 1, 2, 3. So I'm going to, every line is a half unit. So negative 1.24 puts me here. Negative 1.63, that puts me about right there. And positive, can go a little bit further out. About right there. And then positive 1.24, negative 1.63. Wow. And I can't read my own graph today. Negative 1.24, negative 1.63. Jeez. Alright, so I have my 3 points, and the graph looks roughly that it's a sketch. On the test, I would just be concerned about those 3 values being fairly accurate. Increasing intervals, so this graph is increasing here and here, and it's decreasing here and here. So increasing intervals are negative 1.24 to 0 and positive 1.24 to infinity, and it's decreasing from negative infinity to negative 1.24 and from 0 to 1.24. And just by looking at this, it appears to be reflecting across the y-axis, so this is an even function. Alright, find each of the following. These are compositions. So k of h of x. So remember, again, just like with inverses, with compositions, if I am manipulating a function, I have to look at the domain. So looking at k and h real quick, k is not defined when x is 0, and h, if I solve the inside of this real quick, h has to be less than or equal to 1. If you do some quick math, 2 minus 2x is less than or is greater than or equal to 0. Subtract the 2 divided by negative 2, which makes me flip the inequality around. So I have to keep these 2 things in mind when we find this composition. So I'm going to plug h into k. So I get 1 over the square root of 2 minus 2x squared. So we know the square and the square root will cancel, so I get 1 over 2 minus 2x. That is my composition, k of h. But now we have a domain problem. This does not look like we have a domain problem necessarily. But we go back up to h and k, and again we're looking for the least restrictive. So we have h has to be less than or equal to 1, and k cannot be 0. So we can go from negative infinity until 0. We stop at 0, and we can go from 0 all the way up until positive 1. And that is my composition of functions. G of f, so I look at g, that's a polynomial, that's fine, that's all real numbers. F is a polynomial, that's fine, that's all real numbers, so I just have to plug f into g. So I'm going to have 5x plus 3 squared plus 5 times 5x plus 3 plus 6. I get 25x squared plus 30x plus 9 plus 25x plus 15 plus 6. Combine some like terms. 25x squared plus 55x plus 30 in my domain. all real numbers. Didn't necessarily have to state it because it wasn't an issue, but I did anyway. J of 3. So because I'm plugging in a value, I don't need to necessarily worry about the domain restrictions. I'm just going to plug the value in, and I'm going to start by plugging 3 into the first J, and then get that output and plug that into the second J. So I'm going to find J of 3. So J is the square root of 3 squared minus 1, so that's going to be the square root of 8. Now 8 is my input that I'm going to plug in, so I'm now going to find J. I have no idea what just happened. I'm going to plug in J of the square root of 8 now. That's going to be the square root of the square root of 8 squared minus 1. Those cancel out. I get the square root of 7. And finally, last problem, K of F. So again, I'm going to plug -2 into F, get that output, plug that into K. So F of -2 is going to be 5 times -2 plus 3, which is -7. Now -7 is my, that wasn't an answer. I'm going to plug the -7 into K. So it's going to be K of -7. So I get 1 over -7 squared, which is 1 over 49. So there's my composition. So that's it. That's the entire practice test. Make sure you do the book work, and you should be ready to go for the test on Thursday.